Buenos dias, Puebla. Thanks for having me here. So in the next 40 minutes, I'm going to take you to a travel that touches quantum mechanics, artificial intelligence, machine learning, and genomics. So put your helmet on, buckle up, and we're going to try to make it in time. So the idea of discovering how life works is probably the oldest achievement that humans are trying to pursue. But in 1905, everything changed. Erwin Schrödinger, a young physicist, started to understand that there must be a code that defines what we are. Rosalind Franklin decided to crystallize a human cell following this advice, and she saw for the first time the famous X picture. That was our code, the DNA. Watson and Crick started to understand it. They took a Nobel Prize for it, but it took us 40 years, from 1960 to the beginning of this millennia, for a man, Craig Venter, to tap inside the human cell, unpack all this gigantic code, and read it. For the first time, in year 2000, we became the first species on this planet able to read their own source code, able to read the instruction manual that assembled us. Now, to engage a little bit on how this alphabet works, I decided to take here something very personal. What you see in the screen, it's me. This is a piece of me. This is specifically a piece that allows me to have emotions, okay? And since I'm Italian, it's a large piece. But so to assemble an entire human being, you need about 3 billion of these letters. This makes a human. How many are 3 billion? Are there many? Are there little? We decided at the beginning of this year to give a visual perception on how large is this instruction manual, to print it. And a human being printed at character 6 happens to take 262,420 pages. So this is the largest instruction manual that you can find in your life, and no matter how proficient you are assembling Swedish furniture, this thing is nothing you can read or nothing you can understand with our brain capacity. So the biggest challenge of this millennia is starting to crack this code. What a specific letter that I show you does, and how a difference makes us this population that we coexist with. So there are 3 technologies, 3 approaches. I'm going to take you in 2 of them. One is the lab, and it's the oldest and still the most valid approach. It's the very final step. We try to change letters, and we try to understand how smaller species evolve, bacteria. We did it for a long time. But it's hard to do it with humans, and it's very slow. But in the last years, new technologies came in place: computing, artificial intelligence, we talked this morning, and high-performance computing. So what I'm going to show you are a couple of results on how we are starting to interpret this code better and better in time. So artificial intelligence is a very basic, very brutally, the approach is, okay, I forget to make a sense in a mechanicistic way on how this thing works, but I'm going to try to teach a machine to read this code, to read this book, and find the signal. So to do this, the first thing that you need to do is assembling a gigantic database. And that was the idea of Craig and Peter Diamandis. They started a new company sequencing the largest number of humans that has ever been sequenced. On one side, we sequenced tens of thousands of human beings. We extracted the DNA and all the books of thousands and thousands of humans. On the other side, we collected their phenotype. Their phenotype is a technical term that defines whatever you see in a human, either your physical traits or the specific development of a disease or some kind of complication and clinically relevant things. So collecting phenotype and collecting genotypes is possible today only thanks to a hyper-exponential decay of cost. To give you an example, at year 2000, the first human genome that we sequenced costed $100 million. Today, sequencing one genome, a human being, costs about $1,000. It's a hyper-exponential decay that is making this technology accessible, and every one of us can do it. By the way, how many of you have your genome sequenced? Raise your hands. Okay, I count 5. Okay, 7. I don't see over there, but next year, this room has to be full of hands raising, and I'm trying to convince you now why. So the moment we start to access genome, we start to understand and train machines to read weak signals, predicting things. And one of the first examples that we put and we focused on was common traits, just to benchmark how good are we. Common traits are common, so everyone has a color of the eye, everyone has a height. We can try to see how we can get. So we decided at the beginning to predict simple things. Simple. They're not very simple, but something that we perceive as simple. Height, for example. Your height is not only written in your genome. There is 80% of the signal in your genes, but we can reconstruct most of it, 78%. We get to eye color, that we are very precise, 85% precision. BMI, not very good, as you might imagine. Most of it is due to your lifestyle. This is the body mass index, ratio of your weight and your height. But we get 20% of the signal. Skin color, very precise. Age, that was a challenge, scientific challenge. Is your code changing? Does something happen that makes you older? Well, we had a clear clues, and we started to read them. So the telomere contraction, chromosome Y depletion, things that you lose while you age. We can predict your age from your blood with about 6 years of precision. And now the challenge that we ended up was, can we predict a highly complex trait? So can we try to assemble a large learning and predict a human face? So a human face is a complex trait, is coming from millions of sites in your genome. And what we did, we collected thousands of faces, we made a model, an embedding, and we started to see what was the predictability over there. So what you see over here, for example, this is a subject that comes in our lab, is a reduced complexity face. So the moles, the asymmetries are removed. These are not in your genes. They're all coming up from the environment, from your coupling with the environment. And we try to see if we can reconstruct some signal from the genome to get close to this face. And this is a person that has never been part of the training. This is the face that we reproduce. So when I show this face, I always ask for the audience to be a little inspector. So try to check the face. They're not the same person. They're not perfect. And it's important. The model is not perfect. The vast majority of the signal come from your gender, ethnicity, BMI, age. But we get close to a ballpark that makes us confident. This is the person that comes in our lab. This is the prediction. Person that comes in our lab. And this is the prediction. So this technology is getting better and better, and the same thing we're using it for predicting early detection of different class of disease and therapeutics. And we are getting stronger and stronger the more the database is growing. But another approach that I want to show you is a more mechanical one. So machine learning, we are at the top of the books. The machine reads the books, see the faces, or see the signal, and try to make some interpretation out of it. What we lose most of the time with this technique is the reasoning, is why and what mechanically happen and compose the signal. So a second dream that is starting to be real in these years is high-performance computing. So the question is, can we make an atomic-level simulation of you? Can we take this code and reproduce the entire simulation atom by atom of a human being and actually see how everything works in the detail down at the cells? So this is a large dream that we are still far away computationally, but there is a smaller dream that is starting to be incredibly exciting for very different therapeutic domains and is pharmaceuticals in general. So what you see over here is a representation of your cells. This is the surface of one of your cells. And the yellow blob over here that you see is what we call a binding receptor, is a protein, okay? So the very way you exist and the metabolism basically is an exchange of molecules that fit inside that specific hole. It's exactly like a key lock problem, okay? There are thousands of molecules that you use to activate whatever you do to exist. Now, a pharmaceutical is fundamentally a drug, is a chemical that taps a button that we know and that we like to activate or deactivate in a way or in another. Now, what I'm showing you is how good are we getting to try to do pharmaceuticals in an almost digital way. Since we graduated in genomics 10 minutes ago, if there is something in your body, there must be a code. So for that yellow blob, there has to be a code. And there is a code. is a gene. A gene expresses this protein, and this is what you want to target. So can we simulate this problem? Can we try to take your genes and build a protein and see if a drug works good for you or not? Can we do it computationally? So 10 years ago, when I started to do this thing, it was the simulation, and this problem was costing about 1 million of hours of supercomputers. I had to fly in a military facility, rent a gigantic storage of computers, and run one single simulation for one single protein and one single drug. But in the same time, and that's when future is ironic, a completely different industry had a very similar problem mathematically. Nerds, video gamers. For the longest time, in the last 20 years, video gamers developed an entire new industry to make characters snappier, faster, better graphics. This is mathematics at the end, and they built an entire new CPU that is called graphic processing unit to solve this problem faster and cheaper and better. But this is the exact mathematical problem that I need to simulate your proteins. So the next time you see one of your kids playing the Xbox at night, secretly is saving the world in a very indirect way. So what I'm showing you is the results of this approach, how we can do on a small commodity hardware, on an Xbox, a simulation that is starting to be the future of pharmaceutical. Here we have a drug, methotrexate, and the code, DHFR. This is the protein. So what I'm showing you is something for which you all should be interested to do your gene test. Every single drug can potentially work in a different way with different letters of your genome. This is a code, but some of us, instead of having a CG over there, have a TT, small difference. Some of us, instead of having a C, has a G. And some of us have both differences. Now, this drug, which is a chemotherapy used across the border, so works for the standard profile, but for people that have different mutation, works worse than worst. 20 times less, 40 times less, the last part, 650 times less. You don't know which bucket are you in, and unless you have your genome sequence, your doctor will not know. So this is a breakthrough that is starting to show us how drugs are working for your specific body. And what I'm showing you, this line took 10 years of research. We had to find the people doing binding assay, testing and trying, and understanding how the drug works. But thanks to video gamers, we can do this. This is a simulation that runs on an Xbox of your protein and your drug. This is the methotrexate. And we can reconstruct with a very interesting precision how the drug works for your specific protein, for your specific genome. So all these technologies, computation, machine learning, that are happening since hundreds of years. Biology, quantum mechanics, the beginning of the CPU, artificial intelligence, HPC, and genomics. These are a bunch of technologies for which thousands of people are cooperating and working since hundreds of years. And we're not doing for any strange dystopian vision of AI colonization. We are doing it because with these technologies, we can start to tackle and touch disease that we don't know how to cure now. And we are finding better and better cures. We're moving medicine to a personalized, predictive, and precise intelligence industry. And this revolution can happen faster only if every one of us will tap in this, will get ownership of your health, will get sequence, and will scale down these approaches to making democratic for all over the world. This is the future of medicine that I want to see. Thank you. Thank you.